An important application of optimization is in profits. As in the univariate case, our goal is to maximize profits. However, here we have a firm that has two goods, X and Y. The total profit is equal to the revenue obtained from good X plus the revenue obtained from good Y minus the cost function from both goods. Notice that in some occasions we will have the inverse demand for X and Y. The profit maximization is pretty similar as the univariate case. We do first the procedure of the first order condition, in which we take the first partial derivative with respect to X and then with respect to Y, and we set them equals to 0. This procedure will help us to obtain the optimal combination X and Y that optimize the profit function. Then we go and compute the second order condition, in which we need to verify that the function at that point is concave. To ensure that this point is a relative maximum. To do that, we need to ensure that the second partial derivative of the profit with respect to X and the second partial derivative of profit with respect to Y are both less than 0. And on the other hand, that the Hessian condition is satisfied, in which both second partial derivatives multiplying to each other must be greater than the square of the cross partial derivative. Finally, in order to obtain the optimal profit, we just plug in the profit function our critical points. To illustrate how we maximize profits, let's solve the following example. Here we have the anniversary resort, which makes profit from selling two services, the entrance tickets and the restaurant food. Both products face the following inverse linear demands. And we have also the cost function. Here our tasks are first to set the profit function, then to find the combination of X and Y that maximizes the profit, and we need to check that the point is a relative maximum, and finally we will need to calculate the maximum profit. First, we need to set the profit in terms of quantities of X and Y. Remember that profit is equal to the price of X times X plus the price of Y times Y minus the cost function. This is because profit is equal to the revenue obtained from X plus the revenue obtained from Y minus the cost of producing both goods. Here we can use the inverse demand to express the price as a function of quantity. So here we set 120 minus 4x times x plus, instead of the price of y, we write the inverse demand times y minus the cost function, which is 2x squared plus y squared plus 4xy. Now let's proceed with the simplification using algebra. So this is 120x minus 4x squared plus 96y minus 2y squared minus 2x squared minus y squared minus 4xy. Simplifying, we obtain 120x, and then we have here minus 6x squared, then plus 96y, and minus 3y squared minus 4xy. So this is our profit function. Now let's find our critical point x comma y by using the first order condition. In the first order condition, we take the partial derivative with respect to x, which in this case will be 120 minus 12x. The derivative of 96y with respect to x is 0, and the derivative of minus 3y squared with respect to x is also 0 because they do not contain x. Finally, here we have the constant part, which is minus 4y, and then the derivative of x with respect to x is 1. And then we set this equals to 0. Now let's obtain the partial derivative of the profit with respect to y. The first two terms, the derivative is 0 because they do not contain y. Then the next part is 96, and the derivative of 3y squared is 6y. Then here, the constant part is minus 4x times the derivative of the variable part, which is y. The derivative of y with respect to y is simply 1. So 1 times 4x is 4x. And then we set this equals to 0. Because we have two equations and two unknowns, we can solve this problem. The easiest thing that we can do is to divide by 4. In that way, we obtain 30 minus 3x, and in the case of the 4y divided by 4 is y, and we can pass it to the other side, it becomes positive y. So now we have y as a function of x. Let's replace that relationship here. So here we have 96 minus 6 times y, but instead of y, we're going to write 30 minus 3x minus 4x equals 0. So this is 96 minus 180 plus 18x minus 4x equals 0. So this is 18 minus 4 is 14x, and then 96 minus 180 is minus 84. We can pass it to the right hand side as positive 84. So this means that x is equals to 6. If x is equals to 6, then y was 30 minus 3 times x, which is 6. This means that y star is 30 minus 18 is 12. So our critical point is 6, 12. In our third step, we need to verify that the point x, y is a relative maximum. And remember, to ensure that the second partial derivative with respect to x and with respect to y both has to be less than 0, and the Hessian condition need to be satisfied. So let's start by finding the second partial with respect to x. So this is simply the partial of pi x. So this is the derivative of the partial with respect to x again. So here we have a constant, so the derivative is 0. Then the derivative of minus 12x with respect to x is simply minus 12. So this is less than 0. So this is verified. Now let's continue with the partial derivative with respect to y now. So the second partial derivative with respect to y is simply the derivative with respect to y of pi y. In this case, the derivative of the constant is 0 again, and the derivative with respect to y here is minus 6. Then the derivative of minus 4x with respect to y is simply 0, because there is no y in this term. And as you can see here, this is also less than 0. Now let's find the cross partial. For the cross partial, this is the derivative of pi x with respect to y. In that case, these first two terms, the derivative with respect to y is 0, and then we obtain minus 4, because that is the constant part, which is minus 4, and then the derivative of y with respect to y is 1. Now let's proceed to verify the Hessian condition. So pi xx times pi yy must be greater than pi xy squared. Pi xx is minus 12 times pi yy is minus 6, and the cross partial derivative of the profit square, which is minus 4 squared. So this is 72, and this is 16. And as you can see, 72 is greater than 16, so this is verified. Because the three conditions are satisfied, we can conclude that this point is a relative maximum. The last step is simply to calculate the optimal profit by plugging in the profit function our relative maximum point. So here, let's plug the values. So this is 120x, and x was equals to 6 minus 6 times x squared plus 96 times y, and y, remember, that was 12, minus 3 times 12 squared minus 4 times xy, so it's times 6 times 12. This means that the optimal profit, inserting the values of x equals 6 and y equals 12 is equals to 930. So this is our optimal profit.